Hey everybody. In this video today, we will be using derivatives to find the concavity of a function and also its points of inflection. So we're given a function f of x equals 2x cubed plus 3x squared plus 1. We went over this in the last learning target 16, in the other video as well. So determining the increasing and decreasing intervals of that. So check that out. That would be helpful for this. But we can still solve it independently. So when we're looking for inflection points in concavity, we think second derivative in this case. But first, we still need to take the first derivative, which is pretty simple just using the power rule, 6x squared plus 6x. And then we need to take a second derivative, f double prime of x. That's just equal to 12x plus 6. And similar to finding the increasing and decreasing intervals of a function, we want to set this second derivative equal to 0 and solve for x. In this case, easy enough. X is going to be equal to negative 1/2. That's our possible inflection point. So once again, we're going to use a sign chart. This indicates the x-axis. We'll be looking at the sine of f double prime in this case. And we'll use that to determine the behavior of our function f. So we're going to mark our root that we found of negative 1/2. In this situation, we only need to consider the two regions, the left and to the right. Easy enough. We can choose nice whole numbers as our test values. So I'm going to go with negative 1 and 0 as our test values. Alrighty then. So we'll plug our test values into our second derivative. So we will have negative 1 into 12x plus 6, which gives us negative 12 plus 6, which is negative 6, which is a negative. Then plugging 0 into f double prime, we'll just get 6, which is a positive. Easy enough with really with just one factor here. So from there, we can determine the behavior on similar lines to increasing and decreasing intervals. If we have a negative f double prime, that means we have concave down. You also write like CC down arrows, CC down, whatever works, as long as you get the point across. And then here we will have concave up because it's positive f double prime. Similar to the last video, we'll have to really make sure we explain the concavity. So we'll say f is concave up on the interval from negative 1/2 to infinity, and concave down on the interval negative infinity to negative 1/2. Just to clarify, so concave up from here going that way, and then concave down all the way from negative infinity to negative 1/2. I touched on the last video as well. Very important to use parentheses here. At the 0 value, that's where f double prime is equal to 0. So it won't be concave up, nor will it be concave down. It's neither. So that's why we don't include it in our interval. Hence the parentheses, which are not inclusive. So that's the answer to part A. Now let's take a look at B. We need to find the points of inflection. In this case, it says points, but we really only have one potential point, x equals negative 1/2. So I'll write that down. We know that f changes concavity. Sorry for my bad handwriting. X equals negative 1/2. So we'll plug that into our function f and determine the y value that corresponds to this inflection point. I have f of negative 1/2. Let me bring down that function as well, just for reference here. We know that f of x equals 2x cubed plus 3x squared plus 1. We did all that hard work doing these derivatives. We don't want to get points off for just forgetting what the actual function is. So we'll have 2 times negative 1/2 cubed plus 3 negative 1/2 squared plus 1. All right, a little bit of arithmetic here. So if I have a negative 1/2 times a negative 1/2 times a negative 1/2, I'll end up with a negative still, a negative 1/8. There's the 2 times 2 times 2 in the denominator. So similarly, we have negative 1/2 squared. That's negative 1/2 times negative 1/2, or just 1/4. Then just that 1. All right, simplifying even more. 2 times negative 1/8, negative 1/4. 3 times 1/4 is 3/4 plus 1, almost there. Negative 1/4 plus 3/4. That's going to be positive 2/4, which is the same as 1/2 plus 1. That is equal to 3/2. Oof. All right, now we can say that our inflection point is at negative 1/2 our x value, 3/2 our y value. All right, summarizing this a little bit more. Once again, pretty similar to the increasing and decreasing problem that we did in learning target 16. But we take our first derivative. We also need to take a second derivative. We set that second derivative equal to 0 to get a potential inflection point. We do our sign chart and determine the sign of f double prime. That corresponds with the concavity for a certain region. We make sure we write it out in good solid English, describing when it's concave up and concave down, using parentheses, because it's not going to be including those zeros. Then to find the points of inflection, we take our points where the concavity changed, determined in the step before, and then we just plug that into our function. And after doing a bit of math, we get our y value, and then we need to write it out, the actual point, inflection point, at negative 1/2, 3/2.